Thank you very much, dear expert teacher, for accepting my paper. Today, my topic is about performance analysis of indoor visible light ACO-OFDM coding. My name is Pengyuan Chen, and my corresponding author's name is Ping Li. I'm from Research Institute of Photonics, Dalian Polytechnic University. That's my introduction. Visible light communication technologies use fluorescent light of light-emitting diodes to send out high-speed flickering signals that are invisible to naked eye to transmit information. It has the advantages of rich spectral resource, low consumption, low cost, and good confidently. With the popularity and repeat development of light-emitting diodes, LED-based lighting and display systems have become more and more integrated into people's lives, and visible light communication technology has become one of the fastest growing high-tech fields in today's society. In order to realize the effectiveness and reliable of data transmission in the visible light communication systems, this article introduced an ACO-OFDM technology and adds China coding to the visible light communication system to improve the system's error detection and correction capabilities. First, the article explained the general system framework of the visible light communication systems. Second, the article explains the working principle of ACO-OFDM technology and Hermitian mapping, and simulate the ACO-OFDM systems under the visible light channel and compare the ACO-OFDM and 4 ppm, BPSK, QPSK, and 16 QAM bit error rate simulation comparison. Then, this article briefly introduced the linear block code, BCH coding, and convolutional code, 3-channel coding techniques, and 3 coding techniques for bit error rate comparison simulation. Finally, a modulation and channel code technology more suitable for visible light communication is selected. That's principle of visible light communication. The visible light communication system structure is shown in Figure 1. It can be seen that, similar to the traditional radio frequency communication systems, the visible light communication system is also divided into 3 parts: visible light communication transmitter, visible light communication wireless channel, and visible communication receiver. The specific functions of each part are as follows. The first is visible light communication transmitter. The original signal is a binary bit stream. First, pre-processing, coding, and modulation is performed. That is, an error correction code is added to original signal to be transmitted, and An appropriate modulation method is selected to improve the error correcting capability and reliability of the transmission signal. After LED is driving, the electrical signal converted into an optical signal, and after passing through the LED device, the electrical energy is converted into light energy and emitting. Among them, the light source use the optical communication systems can be a white LED. The second is visible light communication receiver. The main device at the receiving end is detector, which can perform optical conversion of the signal. After optical signal is converted into electrical signal, it's demodulated and decoded corresponding to the transmitting end to restore the original signal. Third, that is ACO-OFDM technology. OFDM is one of the multi-carrier modulation technologies. The so-called OFDM technology is to divide the data stream to be transmitting into several sub-data streams. Each sub-data stream has a much lower transmission bit rate, and the sub-data streams are used to modulate several mutually orthogonal carrier in parallel. The OFDM signal is a bipolar signal, but for the traditional intensity modulation, direct detection of optical communication system, the bipolar signal cannot be directly used because the light intensity cannot appear negative. Therefore, for optical OFDM, the usual solution is to add a DC bias to the OFDM signal during electrical optical signal conversion, so that bipolar signal becomes a unipolar signal, which can be transmitted on light. However, the use of DC bias OFDM will increase the average optical power of the transmitted optical signal while reducing the modulation depth, resulting in low power efficiency of the system. Now, a new ACO-OFDM method can be used to solve the problem of bipolar OFDM signals. ACO-OFDM is concerned to cut off the part of the original OFDM signal, and that is less than 0, leaving only positive values. Figure 2 shows that the specific process of the ACO-OFDM system is at the transmitted end. The original signal is first subjected to channel coding and PSK or QAM modulation. The mapping signal is serial parallel converted into parallel data stream, and the pilot signal is inserted Hermitian mapping IFFT using a cyclic prefix, theoring the negative part of the signal, and then converting it into a serial data stream. forming an ACO-OFDM symbol and transmitting it into the wireless channel. When a signal is detected at the receiving end, the signal is first converted into a parallel data stream. The cycle prefix is removed, and the parallel data stream is converted into a serial data stream after FFT. At this time, the PSK or QEM modulated data is obtained. The original data can be obtained by corresponding demodulation. Hermitian mapping. In order to complete symbol become a position real single after fast Fourier transform, it's necessary to process the single, that is, Hermit mapping operation, so that the single can meet in the following formula, where xk is a complex conjugate expression of xk. The complex signal satisfying the central conjugate symmetry is output to real signal after IFFT transform. Then is a grid interval and cycle prefix. In the OFDM system, inserting a interval between OFDM single can eliminate inter-symbol interference to the greatest extent. The length of this guard interval is generally greater than the maximum delay extension of the wireless channel, so that the component of a simple generated by multipath propagation is not will interfere with the next symbol. In the guard interval, it is not necessary to add a single, that is, the guard interval is a blank transmission time. However, in the OFDM system, due to multipath propagation, the blank guard interval will cause inter-channel interference, which will cause the gap between the subcarriers. The destruction of the cause interference between different subcarriers. As a result, the original OFDM single with a width of t can be periodically extended using the extend single as a guard interval. As shown in Figure 3, the signal in the guard interval is called the cyclic prefix. The signal of the cyclic prefix is the same as the part of the tail time of the OFDM single. The OFDM symbol transmitted in this way is at the receiving end, and the part with the initial time is first removed, and the remaining part with a width of t is Fourier transformed and then demodulated in the process of time domain convolution. The privacy of OFDM symbols can be well protected by adding a cyclic prefix, and the ICI of other subcarriers is reduced or eliminated. And that's my ACO-OFDM system simulation. This article used Simulink software to build an ACO-OFDM system. The model is shown in Figure 4. The source simple timing is 128 subdata carriers, 512 point FFT, cyclic prefix legends 16, 1024 OFDM symbols, and the bit error rate statistics modulate accept extension as shown is Figure 5. The original signal transmitted by the source is transmitted to the white spotlight communication channel after different modulation methods. And after demodulation, the OFDM system has the lattice-based error rate and the PPM system, the bit error rate of the BPSK system and the QPX system is basically the same. The 16QAM system has the highest bit error rate, and with the increase of the signal-to-noise ratio, the decrease is not large. So, in terms of the bit error rate, the modulation method adopts ACO-OFDM technology. The white spotlight communication system had the lowest performance. Due to the interference and the filling-in channel during the transmission of the digital signal, error codes are generated in the transmit data stream, thereby causing signal distortion and at the receiving end. Therefore, through the link of channel coding, the digital signal adopts error and error directions coding technology, and the data stream is proceeding accordingly, so that systems have a certain error correctability and anti-interference ability, which can greatly avoid bit errors in the code stream transmission happened. First is linear block code. Linear block codes are received by NKD. In the code legends, there is many distance of the code, and K is the legends of information group. Linear block code encoding requires two matrices. One, the generation matrix represented by G, and the other is the check matrix represented by H. And the second is BCH code. The BCH code is linear block code in a finite field, which has ability to correct multiple random errors. The third is convolutional code. Convolutional code NKN is a non-blocking code, although convolutional codes also encode k-bit information segments into n-bit code groups. The supervision symbols are not only related to the current k-bit information segments, but also the same as the previous n information. This article used Simulink to build an ACO-OFDM system using linear block codes, BCH code, and convolution codes, and compares the bit error rates of different code methods. It can be seen from Figure 7 that after the signal generated by the source is subjected to different encoding methods, ACO-OFDM systems and corresponding decoding when the channel signal-to-noise ratio is greater than 28 dB. Concluding remarks. This article briefly introduced the general system framework and channel mode of visible light communication, and explained the principle of ACO-OFDM system and PPM system, Hermitian mapping, and cyclic prefix. Cyclic is used to simulate the visible light communication system based on ACO-OFDM technology and PPM modulation technology, and compares the analyze the bit error rate with BPSK, QPSK, and 16QAM. The experimental results verify the feasibility of ACO-OFDM technology in visible light communication system and the relatively low bit error rate performance. ACO-OFDM technology, compared with other modulation methods, it has strong anti-fading ability, high spectral utilization, suitable of high-speed data transmission, simple modulation and demodulation, no complex equalization technology at the receiving end, and strong anti-inter-simple interference ability. Advantages. OFDM technology as the modulation method of visible light communication system has more advantages after that. This article introduce the principle and compare and simulate the three coding methods of linear block code, BCH code, and convolutional code. It concludes that ACO-OFDM system based on convolution code channel coding is more suitable for the choice of visible light communication system. And that's my reference. That's the end of my report. Thanks.